Today we're going to learn how to simplify radicals. So before we begin, we're going to review what prime factorization is. So prime factorization is when you write all the factors of a number and you break down those factors as far as possible until you get prime numbers. So a good way to do that would be to be factor trees, and then once you have completely factored the number using the factor tree, you look at those last numbers and then you write any repeating factors as a base with an exponent based on how many times it repeated. So for example, 48, if you used a factor tree, you would end up with 2 times 2 times 2 times 2 times 3. Well, because there are 4 2's, we're going to write 2 to the 4th times 3. And then 210, if we were to break that down using a factor tree, that would become 2 times 3 times 5 times 7. And then 297 would be 3 times 3 times 3 times 11. And since the 3 repeated 3 times, we're going to rewrite it as 3 to the 3rd times 11. So looking at these numbers, these are a little bit bigger, so 600 would be rewritten. If we factored 600, it would be 2 times 2 times 2 times 3 times 5 times 5. So we would rewrite those 3 2's as 2 to the 3rd, and we would rewrite those 2 5's as 5 to the 2nd. So our prime factorization would be 2 to the 3rd times 3 times 5 squared. 875 would be 5 times 5 times 5 times 7, so we would rewrite it as 5 to the 3rd power times 7. So when we're simplifying radicals, what we're doing is that we are rewriting in simplest form. So whenever we learned fractions, we always made sure that our fractions was in lowest terms. So for example, if you had 3 over 6, you would rewrite it as 1 over 2. So you wrote an equivalent expression for that fraction. It was just in simplest forms. So when we're simplifying radicals, we're doing the same things. Our answers should be equivalent. It's just that they should be equivalent. It's just that they should be in simplest form. So when the radical is in simplest form, this is how you know it's in simplest form. The radicand, which is the expression under the radical symbol, is going to have no perfect power factors. So remember, perfect power factors are those perfect squares and perfect cubes that we had talked about. We shouldn't have any factors that are perfect squares or perfect cubes if our radical is in simplest form. So before we begin, we're going to learn a new property. It's called the product property of radicals. So what this is saying is that if you have a product in your radicand, which is the expression underneath the radical symbol, so for example, x times y is in the radicand and it's a product, then based on the product property, you're going to be able to separate that into 2 different radicals that are being multiplied by each other. So you notice that this was a product, and it's still a product. It's just that you were able to separate those into their own radicals. So let's look at an example. If we have the square root of 24 and we rewrote the square root of 24 as prime factors, it would be 2 times 2 times 2 times 3. Well, I know that 2 times 2, that's a perfect square. So I'm going to separate the 2 times 2, which is 2 squared, into its own radical, and then 2 times 3, I'm going to put in the other radical. So notice that they're still being multiplied together. Well, now that I have the square root of 2 squared, well, that simplifies. We learned that in the previous lesson, that just becomes 2. So now I have a simplified radical of 2 square roots of 6. So the square root of 75, if I were to write the prime factorization of 75, it would be 3 times 5 times 5. Well, 5 times 5 is a perfect square, so I'm going to isolate it in its own radical, and then the other radical, which is being multiplied, I'm going to have the 3 that's left over. Well, the square root of 5 squared becomes 5, so my final answer becomes 5 square roots of 3. So for this one, I'm looking for the cubed root of 40. So now I'm not looking for perfect squares, but I'm looking for perfect cubes. So if I were to rewrite 40 as a prime factorization, it would be 2 times 2 times 2 times 5. Well, 2 times 2 times 2, that's a perfect cube. So I'm going to separate it. And so I have 2 cubed and 1 radical, and I have the 5 in the other radical, and they're still being multiplied. But now that I know that I have cubed roots, so 2 cubed, that just becomes 2, and I'm left with 2 cubed roots of 5. So when you are simplifying radicals, these will be your steps. So step 1, write the radicand as the product of its prime factors. So once you write your radicand as a product of factors, you can easily tell and identify your perfect powers. The second step is going to apply that product property to separate those perfect powers to their own radical. And your third step is simplify the roots of the perfect powers. So once you have your perfect powers isolated, they simplify and become just the expression under the radical symbol, the radicand. Last step is multiply the factors inside and outside of the radical. So this happens whenever you pull multiple things outside of the radical, or you are left with multiple things inside the radical. You'll have to multiply them. So let's look at an example. We have the square root of 648. So if I were to write the prime factorization, it would be 2 times 2 times 2 times 3 times 3 times 3 times 3. So the first thing I want to do is I want to separate my perfect squares. I'm doing perfect squares because I don't have an index here, which means that we're doing the square root. So I'm looking for perfect squares. So these two 2's become 2 squared. And these 3 3's will become 3 squared. And then these 2 3's will become 3 squared. And then this 2 is kind of by himself. He doesn't have anyone to partner with. So if I have the square root of 2 squared, that becomes 2. And then the square root of 3 squared becomes 3. And the square root of 3 squared becomes 3. And then, of course, I'm left with the square root of 2, which was not able to simplify. But notice on the outside, I now have 2 times 3 times 3, which I can go ahead and multiply. It becomes 18. So my final answer is 18 square roots of 2. Let's look at another example, the cubed root of 14,580. So after my prime factorization, I'm left with 2 times 2 times 3 times 3 times 3 times 3 times 3 times 3 times 5. So since I'm doing the cubed root, I'm looking for perfect cubes. So these 3 3's will make a cubed root, and these 3 3's will make a cubed root. So I'm going to separate those. So here's my first set of 3's and my second set of 3's. But then I'm left with a 2, a 2, and a 5. So that's what's left in this radical. So the cubed root of 3 cubed becomes 3. So I have 1 3. I have another cubed root of 3 cubed. So here's that 3. And then 2 times 2 times 5 is 20. So I'm left with 3 roots of 20. And then I can simplify 3 times 3, which is 9. So my final answer becomes 9 cubed roots of 20. So let's talk about even and odd roots. So if our index is even, so an even root, so like a square root or a fourth root or a sixth root, and the radical contains variables, so like x's and y's, then we have to make sure that we're using absolute value. So for example, if we do the square root of x squared, we actually have the absolute value of x. Now, if the index is odd, an odd root, such as the cube root or the fifth root or the seventh root, then we don't have to use the absolute value symbol. So, for example, if I have the cube root of x cubed, I can just write x. So remember, we only have to do this when we're using variables. So if we have the nth root of x to the n, so it looks like this, right? We're taking the root of the variable with that same power. Then we're going to end up with the absolute value of x if our root is even, or we're going to end up with just x if n is odd. So let's look at the square root of 32x cubed y squared. So first of all, we rewrite 32. So 32 is 16 times 2, and 16 is a perfect square. And then x cubed can be rewritten as x squared times x. And then, of course, y squared is a perfect square, so it gets its own radical. So the square root of 16 is 4. The square root of x squared, since this is an even index, we actually have to use the absolute value of x. And then the square root of y squared, well, since it's an even index, we have to use the absolute value of y. And then we have the square root of 2x, which we cannot take the square root of. So our final answer is 4x, absolute value of y, 2 to the x. So you might be wondering, why did we no longer have to use the absolute value of x and can just write x? However, we kept the absolute value of y. We're going to get into that in just a moment. So before we talk about how we lost that absolute value, let's do another example. So this is the cube root of 16x squared y to the 4th z to the 6th. So since this is an odd root, we do not have to worry about absolute values. So 16 can be rewritten as 8 times 2, and 8 is a perfect cube, so he's going to be separated. X squared is not a perfect cube, but y to the 4th can be rewritten as y cubed times y, so that gives us a perfect cube right there. And then z to the 6th can be rewritten as z cubed times z cubed, so that gives us 2 perfect cubes right there. So when we simplify, we're going to rewrite it so that all of our perfect cubes are in one radical and all of our non-perfect cubes are in another radical. So when we have all of our perfect cubes in one radical, we can actually follow with the operation. The cube root of 8 becomes 2, the cube root of y cubed becomes y, the cube root of z cubed becomes z, and the cube root of this z cubed also becomes z. And then, of course, we can't simplify this radical because we are no longer have any cube roots. So 2yzz, actually the z times z becomes z squared. So our final simplified answer looks like this, 2yz squared, the cube root of 2x squared y. All right, so let's talk about why we lost that absolute value on that x in that example 3. So the absolute value is not always required for even roots. So remember how we talked about if we had an even index, that's when we use our absolute value? Well, there are some cases where we actually don't have to use it, even if it's an even root. It's only necessary to use that absolute value if the variable raised is an even power. So if you have an even index and you have an odd variable, like an odd power of a variable, you don't have to use an absolute value. You only have to use the absolute value when you have an even index and an even power. So let's look at an example. The square root of x squared has to be the absolute value of x because our index is even and so is our power. Now, if we have the square root of x cubed, that's going to become x square root of x, but that x does not have to be the absolute value of x because even though our index was even, our power was odd, so we don't have to use the absolute value. And then the square root of x to the 4th becomes x squared. And the reason why x to the 4th is x squared times x squared. So when you take the absolute value, you get x times x, which ends up being x squared. And then x to the 5th, the square root of x to the 5th becomes x squared times x. Because x to the 5th has the x to the 4th, which this is x squared. And so that's how we know this is x squared, leaving you just the square root of x. And then x to the 6 is going to become the absolute value of x cubed. And the reason why is because x to the 6 is the same as saying x to the 4th times x squared. Well, x to the 4th we know is x squared. However, x to the square root of x squared is the absolute value of x. So we know that's going to be the absolute value of x. So we have x to the 1st here, but we have x squared here, so there's a total of 3. So it becomes absolute value of x cubed. So last one, the absolute value of x to the 7th. So for this one, we have x to the 4th and x cubed. So x to the 4th is x squared, and x cubed becomes x times the square root of x. So x cubed times x is x cubed, and then we still have this absolute value of x. Or no, I'm sorry, square root of x. And there won't be any absolute value because even though this is an even index, this is an odd power.